we're ready to explain why the black-white procedure described before gives the minimum weight spanning tree. So let's see how that goes. The setup is that we have a connected graph, G, a simple graph, and weighted. And for simplicity, we're going to assume that all the edges have different weights. It's not much of a restriction, and I'll maybe comment about that at the end, but it's not really important. We can assume harmlessly that all of the edges have different weights. And what we're going to do, as before, is we're going to arbitrarily color the vertices of the graph black or white. The only constraint is that there has to be at least one black and at least one white. There's no notion of connected components or anything like that. This is just pure vertices. Every vertex gets arbitrarily assigned a black or white. As long as there's one of each color, that is considered to be an adequate black-white coloring. Okay. Given such a coloring, a gray edge, as before, simply consists of an edge with different colored endpoints. That is, one end is white and the other end is black. Now notice there has to be such an edge because the graph is connected and there are vertices of two different colors. So there's got to be a path between the two vertices of different colors, and that means that there has to be a gray edge on the path in order to change from one color to the other. So there is a gray edge for any legitimate coloring. And that means that there's going to be a minimum weight gray edge. And by our hypothesis that all the edge weights are distinct, there's going to be a unique minimum weight gray edge for that gray coloring, for that black-white coloring. We'll call it E. And the main theorem is that E, it has to be an edge of every minimum weight spanning tree. If E is a minimum weight gray edge for any black-white coloring, it's got to be in the min-weight tree. So every possible minimum weight gray edge is necessarily part of the minimum weight spanning tree. That's a powerful result, puts a lot of restrictions on. But we know even more. We know that there is a spanning tree that's built of the min-weight gray edges. We saw that previously, what the process was of successively finding a new gray edge when you color the different components solidly. Each component gets one color, and that guarantees that any gray edge is going to be a new gray edge. So that tells us that, in fact, there are enough minimum weight gray edges to make a tree. So you put together that they have to be there and they can be there. The conclusion is that, in fact, there is a unique minimum weight spanning tree, and it consists precisely of the minimum weight gray edges under all possible black-white colorings. The minimum weight gray edges form the minimum weight spanning tree. Very cool theorem. And explains all these different algorithms for trying to find a minimum weight spanning tree. Now, the crux of the theorem follows from an easy lemma, which I'm about to state, which I'm calling the swap lemma. And the swap lemma says that if you take any connected spanning subgraph of G, so remember, connected spanning subgraph means C contains every vertex of G, and C is connected. G itself is a connected spanning subgraph of G, but there may be lots of others. We expect the minimum weight spanning tree, or any spanning tree, is going to be a connected spanning subgraph, but I don't care if it's a tree or not. Just give me any connected spanning subgraph C. And suppose that this minimum weight edge E is not an edge of C. Then I claim that there is another edge G in C, and E is lighter than G. And if you remove G and add E to C, you get another still connected spanning tree, spanning subgraph. And because the weight of E is less than the weight of G, it follows that the original C is not minimum, because C, when I take away the heavy edge and add in the light edge, it's smaller. So I've just shown you that if I have a connected spanning subgraph that doesn't have this minimum weight gray edge, then there's another smaller one. So the original that I started with can't be minimum. And that says that E is necessarily a member of any minimum weight connected spanning subgraph. It proves again that the theorem that we were claiming, that every gray edge is necessary. We've finished proving the main theorem if we can prove the swap lemma. Well, let's restate the swap lemma to remember what we're aiming for. The swap lemma says that if you give me any connected spanning subgraph C and it doesn't contain our min-white gray edge E, then there's another edge that I can find in C that's heavier than E, and C minus G plus E is still connected. That's what I gotta prove. I have to find this given C, I have to find this edge G that's heavier than E and that I can take away and still leave a piece that's connected. And the trick is going to be, I'm going to find a gray edge. So the gray edge, if G is a gray edge, then I know it's going to be heavier than E because E is the lightest weight gray edge. Well, let's look at the setup we have. So E is our gray edge that's minimum weight. It connects two vertices, call them U and V. All right? Now, the C that we're talking about is a connected spanning subgraph. So that means that if it doesn't have edge E, there's got to be a path between these two vertices, U and V, because C is connected. So there's some path between U and V in this graph, subgraph C. And so here's our picture. There's the edge E connecting two vertices we're calling U and V. And there's the path in the connected subgraph C that connects U and V. Okay, now here's the elegant argument. Look at this path. It starts at white and ends at black. It's got endpoints of different colors. It has to have a gray edge. Yeah? That's going to be G. Now, of course, as soon as I find a gray edge in C on this path, I know it's going to be heavier than E, so I've satisfied the main criterion, which is it has to be heavier. And what happens if I remove G? Okay, so E is heavier. If I remove G, so I break the path and take away E, but I add back in E, this is the new structure I'm dealing with. The claim is that C minus G plus E is still connected. Yeah? C minus G is still connected. And why is that? Well, the endpoints of G are connected by a path. The only danger in the only way that C minus G could fail to be connected is that when I remove the edge G, the endpoints of G, which used to be connected by G, might not be connected before. But if they are connected, then everything else is connected as it was before. The whole thing stays connected. But the endpoints of G are, after all, connected by a path because I removed G, but I added E, so I could take the pieces of path that included G, and there's a nice path between the endpoints U and V, the endpoints of the G that I removed. The result is I've argued that C minus G plus E is connected as claimed, and I've proved the swap lemma, and I've finished the whole story.